Today we're going to go ahead and journey out into this world of graphing. In Algebra 2, you have to graph more than lines. You actually graph lots of pictures. And we're going to start today by learning how to graph absolute value. Before we start our actual graphing, I just want to talk about what a vertex is. A vertex is, depending on the graph, either the lowest or the highest point on that graph. So if you notice right here, we have two curves that come out of this circle. We have a curve on the left and a curve on the right. So when you have like two curves come together like that, you have yourself a vertex. So you can see right now, the vertex is the lowest point. If I give you a different graph, you can see that the vertex is actually on top. So now the vertex is the highest point. So whether it's the highest or lowest, that's going to be dependent on how the graph is drawn. And then for the last one, you can see we have two lines that come together. Right here is the tip of that. That's called the vertex as well. And you can see that that's clearly the lowest point on the graph. Now what you want to notice is the vertex is the location, right? So for example, this vertex is at 0, 0, the x value is 0, and the y value is 0. So to give that a special name, we're going to use the letters h and k. There's lots of x's and there's lots of y's. On a coordinate plane, we want the vertex to stick out away from the crowd. So we're going to call the vertex the letters h and k, but you need to keep in the back of your mind that h is really an x coordinate and k is really a y coordinate, just very special x and y's, so therefore we give them special letters. All right, the same is true when we did lines, mx plus b. If you remember, b stands for the y-intercept. Well, the y-intercept is really just a y value, but because it's a very special y value, instead of calling it y, we call it b. So in Algebra 1, we learned how to graph lots of lines, and we saw this formula a lot, mx plus b, to the point where now when you see that, you know that's going to make a line, and you just go right into graph mode. And it's going to be the same thing here in Algebra 2. You're going to see a formula, you're going to recognize what kind of formula it is, and you're going to go right into graphing mode, which is what we're doing today. So here's your general formula for an absolute value function. So if you recall, these are absolute value bars. And we just discussed that h and k stand for the x and y coordinate of the vertex, so that we know what those represent. Just like this has an x in the formula, this has an x for a formula. That's like a placeholder for numbers you want to plug in. And if you recall, f of x is really the same thing as saying y. It's just a little bit more fancy notation. That's what we're going to use in this course. So the question is, what does that a represent? And we'll get to that in a little bit. So you're going to go ahead and graph your very first absolute value function. I very much doubt that you have seen it up until now. We don't do that until Algebra 2. So what you do when you have to graph something that you've never graphed before is you make a table, and you pick a couple random numbers to substitute in for x. I always tell my students it's a good idea to use a couple negatives, 0, and a couple positives when you do that. That just gives you a really good idea of the picture of what's going on everywhere. And what we're going to do is we're going to take negative 2, and we're going to plug him into our absolute value formula. So the absolute value of negative 2 is just 2. If you recall, absolute value, the bars, it just means the distance from 0. Negative 2 is 2 spaces from 0. Okay, same thing with negative 1. That's 1 space from 0, and then 0. And even though this is positive 1, it's still 1. 1 is 1 space from 0, and so is 2. And then what we would do is we would pair these all up, and then we would graph all of these ordered pairs, negative 2, 2, negative 1, 1, 0, 0, and so on. And you notice your dots are going to end up making a V. And if I threw more numbers into this table, you would find that those dots would span outwards. So to show that, just draw 2 arrows coming out of that vertex. And what you have right here, you guys, is called the parent absolute value function. So I want you to think of, there's a bunch of different shapes that we can draw. Each of them has to have like an original, right? Just like if you're a gaming person, all right? The very first thing was PlayStation 1, and then PlayStation 2 came out. It was similar to PlayStation 1, but it had a couple extra features, right? And so on from there. But we always start with an original, and that's what this is. So anything that we do to this, we're gonna learn how to move it sideways, up and down. We're gonna make it skinnier. We're gonna make it wider. That's all fine and dandy, but I want you to remember this is where we start with. So it's in comparison to the starting function, to its parent function. All right, so what I would typically have you do in class is use a website called Desmos.com. It's free, it has a graphing calculator, and I would have you type these all in, and what it'll do is it'll graph that for you, and then I would have you copy that down on your paper. Just because this is a video and we don't want to drag this on and on, I'm just going to tell you what Desmos is going to spit out at you. And this right up here. So what would happen is for your first row, your vertexes would all shift to the right. So instead of being at 0, like it was in the last slide, now it's at 2. And then your graph would go up 1 over 1, up 1 over 1, and so on. Same thing here, except your vertex would now be at 3. And your vertex would be at 4. And then what we do is we think, okay, the parent function goes through 0, correct? That's where the parent starts at. So how did this change from that? So compared to where it used to be, this has moved to the right 2 spaces. Okay, again, always remembering the vertex starts at 0, 0, so what happened to it? How did it get over here? So just a simple, it moved to the right. That's all. Now in the section below, you'll find that all your vertexes move to the left. So then we pause and we say, is there some kind of conclusion I can make from what's happening here? It seems that whenever I have a minus inside my bars, it makes my V go to the right. And when I have a plus inside the bars, it makes my V go to the left, which is kind of weird. You would think it would be the opposite. Negative would go left and positive go right. So one thing we want to note is when you're shifting or when you're translating or moving sideways, it's opposite of what you'd think. So plus actually means left and minus actually means right. Then we would use Desmos again to graph this function. You'll notice that I have a negative outside of the bars, and what that's going to do is that's going to make your graph go upside down. Now my graph is drawn incorrectly. It should actually be up here and then that way like that. So just watch out for that. I accidentally bumped mine down 1 space. But you can see that it is upside down from a normal V. It makes my V go upside down. Okay, then we would go back to Desmos and we would graph the next 6 functions. Again, just for the sake of the fact that this is a lesson video, we're trying to speed up time, I'm going to go ahead and put the graphs that Desmos would spit out on the screen for you. So what you'll notice is all my vertexes did not move in these problems. So it looks like when I have a number in front, it does not cause my V to go upside down. It does not cause it to go sideways, but it did tend to make it stretch a little more. So you'll notice up top, your V's are getting closer together. The ends are getting closer together. Whereas on the bottom, when I was using a fraction and then a smaller fraction and then an even smaller fraction, my V is actually getting wider. It's getting closer to the ground. So that's a rule that we want to remember when we're making our rule sheet. When we use these bigger numbers like 2 and 3 and 4 and 5 and 6, it was making our V's more skinny or skinnier. And when we were using fractions and making the fractions go down in value, it made your V get wider. Right, so just some things that I want you to note that we just talked about. Again, when we increase the number in front of the bars, our V will get steeper, or you could say it gets closer, more narrow, however you would word that. But in the second row, my lines were less steep, right? They're very close to hitting the ground, and my V consequently got wider. So all of these things that we just did to our V's, we made the first V's go sideways, and then these V's, the one we made go upside down, and the ones we just did, we made them get skinnier or wider. All of that stuff is called transformations. Each movement is a transformation. So there's 4 main types of transformations that we have to start using, because you're going to be asked to describe what happened, but you want to do it in a mathematical way. So the first kind of movement that we covered is actually called a translation. That's the same thing as saying shift. So we can make our V shift to the left, we can make it shift to the right, we can also make it shift up, and we can make it shift down. So again, that's called a translation. Number 2, reflections is another one. So we did a reflection already. We did have a V that turned upside down. That's also called reflecting about the x-axis. So that's like the more mathematical way to say that. We did not do this yet on Desmos. We won't do this for a while, but you can also make things flip sideways. So we don't just go up and down, we can also go sideways. We can make things go backwards. That's called reflecting across the y-axis. Sometimes people call it a horizontal reflection, same thing. Now, I'm not too picky about word usage in here. If you say translate left 3, that's fine. You can also just say left 3 and I'll get what you're talking about. You don't have to say reflect about the x-axis. You can just say it's upside down. That's fine. I want to know if you memorize the rules with the movements. Now 3 and 4, I am going to be picky about that. We want to get the wordage correctly. So a stretch was when your V got skinnier, right? Which is a little weird because kids are like, yeah, but it's not stretching out. It is stretching from a vertical standpoint. It's getting taller and taller and taller, so it is pulling away from the x-axis. Horizontally, yes, it's getting smaller, but vertically it is getting taller. All right, so when you graphed 3 in front of your bars, that made your V get skinnier. So the way that we word that, we can do a little bit better than saying skinnier, is we say there was a vertical stretch by a factor of 3. Now that gets really annoying to write over and over, so we do come up with abbreviations. So if you would like to use BFO instead of by a factor of, that's fine. But you do really have to have all of this to cover it. Like you can't say stretch, you say vertical stretch. And you can't say just vertical stretch. You have to say by a factor of 3. And then the opposite of stretch would be a shrink. So when your graph got wider, that's called a vertical shrink. So your slope or your graph is getting less steep, and that's what causes it to get wider. And that will typically happen when you have a fraction in front of x, as long as that fraction is below 1 in terms of value. And again, we would phrase that by saying vertical shrink by a factor of a half. And again, if you want to just abbreviate that BFO, that would be fine. So that's kind of our unofficial universal acronym for by a factor of. All right, so again, you really can't identify any transformations until you memorize where the parent function is. So just to close this out, the vertex would be at 0, 0. Right, so we always compare movements to, well, in comparison to where it started at the origin, how did it move? The slope of the right side is going to be 1, so you would just go up 1 over 1, up 1 over 1, up 1 over 1, and connect. And the slope of the left side technically is -1, but usually kids know that because they realize it has to make a V. Right. And then whatever is in front of the bars, that is called your stretch or shrink factor. You can treat that like a slope. So if it says like 1/2 in front, you could go up 1 and write 2. That will work for these, but it will not work for anything else. Right? That counting slope only applies for linear kinds of functions, and an absolute value is consisting of lines. So that will be okay. When we have exponents in our equations, we can't count slope anymore. There's different rules we have to apply. So that's just something to be on the lookout for, and just kind of put that on the back burner just so it's there whenever we get to it. All right, so in our next video, we'll go ahead and actually do some describing and we'll do some graphing.